Okay. Now let's continue. Okay, our review for Maxwell equation. Okay, before we go into the actual light and matter interaction study. Okay. So last time we talked briefly about the Gaussian's law, which came from the Coulomb's law, and then there are two ways to write it. One is that if you include all the charge density, you have the divergence of electrical field. Okay, if you only consider the free charge, and then you put all the other charge, for example, the dipole charge, okay, into the relative permittivity, okay, then you will have a displacement field, okay, and this would be the Gaussian law, and then we will come back here later because like how the displacement field responds, okay, how a light responds to the interact with the matter, okay, is a center subject of this class. And then the next equation we briefly review is a Gaussian law for magnetic field, which simply tells you that there's no magnetic monopole. Okay, and today we're going to quickly look at these two, Faraday induction law, and then this is Ampère law. Okay, and then we'll show you guys. Well, you guys probably already know this, but we'll show you guys again that how you can use these two equations and derive EM field, EM wave, and the speed of light, and then the wave equation. So this curve of the electrical field equals the varying magnetic field. Okay, you're seeing here is called the Faraday equation or Maxwell-Faraday equation, and it came from it came from the experimental observation of Faraday, and then I think originally he actually wrote down a sentence instead of to describe this phenomenon instead of equation. So what he wrote is that you guys can see this in the note, page 4. The Faraday law was that the induced electromotive force, okay, in any closed circuits, for example, there's a closed circuits, the electromotive force is equal to the negative of the time rate of change of magnetic flux, okay, enclosed by the circuits, right? So once you read this, you kind of realize why mathematics is really important, right? Because we kind of have to, because math is really a much more precise way to describe it. So here, okay, what we can see here is that Maxwell actually, kind of translate that into the equation look like this. Okay. This is the electromotive force described by Faraday, which is really just the electrical field. Okay. In any closed circuits, so it's like you do the integration over the entire circuits, right? Over the entire circuits, equal to the time rate of change of the magnetic flux, right? Time rate of change is just d dt, right? This is the differential of time on the magnetic flux. The magnetic flux can be defined in this way: is that if you do a surface integral, okay, surface integral of all the magnetic field, okay, going through this surface, right? Going through this surface. So this is the definition of magnetic flux, and it's time varying, okay, equal to, well, there's a negative sign here, equal to the sum of the electromotive force, okay. And so this is an experimental observation, so you can't really kind of ask why. Okay, this is how this is just the way nature is. And so this is the integration form, but in Maxwell equation, usually people use the differential form. To go from the integration form to the differential form, we'll use the Stokes theorem. Okay, Stokes theorem. What it says is that, okay, if there's enclosed circuits, right? So what you would do is that if you integrate a vector on this circuit, which is similar to what you would have for the Faraday law, okay, this will actually equal to this line integral will actually equal to a surface integral of the curl of the curl of your field, okay, of your vector. And on the first look, it looks like kind of like, not sure where this equation is coming from, but there's actually a very kind of intuitive picture of this. Is that think about if you think about where the magnetic field comes from, you can kind of think of, okay, if there's everywhere there's a little bit of small rings, okay, there's a field like a rotation field here, and then everywhere inside, and then this is this curl, okay, and when you integrate all of them, they will actually cancel each other. If you integrate everywhere on this surface, they will actually cancel each other, and what's left is on the surface. Sorry, what's left is actually on the circuit, right? Because everywhere else you get cancelled. So this is kind of an intuitive picture of why a line integral will equal to a surface integral, okay? And the other way, we can just take it for granted and then just use it here. So what we can do here is that now we can adapt this, we can use this equation and then to plug this into here, and then you will get the line integral of electrical field along the circuits equal to the surface integral of the curl of the electrical field. And then this will equal to, because the Faraday law will equal to minus, right, will equal to the change of the magnetic flux, the rate of change of the magnetic flux. Or you can, and the other way that you can kind of make it easier to look at is that the integration of the magnetic flux is on space, and then the time integral is on time. So these two actually are independent from each other. So you can actually switch the order. You can do the, okay, you can do the time differential first, and then you do the integral of the surface, okay? Now, just like last time, we said that this law is this equation is very general. Okay, it's true for every surface. Okay, for every circuit, every surface. And then the only way that you can have this equation true, okay, hold for any surface is that if these two, okay, if these two variables inside your integration, okay, is the same everywhere, right? So this is why we will get the Maxwell-Faraday law, okay? Okay, like this. Okay. And what this equation really describes is that a time-changing magnetic field will give you electrical field, right? And this is how we generate electric power these days. Okay, since 100 years ago. It's always been this way, unless you use solar power, which would be a very different principles. Okay, and then the one thing that I want to actually emphasize is that the topologically this electrical field generated by the magnetic field is very different from the electrical field generated from a charge, right? So what you have here is that let's say this is magnetic field, and then it's increasing, and then the electrical field you generate will actually form a loop if you draw the electrical line, field line. Okay. As a comparison, your electrical field generated from a charge, okay, will look like this, right? It's not a loop, okay. It actually have a source, right? All the lines actually start from here and then go outside, right? So these two are very, very different, structures. Okay. Any questions here? Okay. One more thing is that if you're not sure about the cross product and then the curl, the definition is in page 5. Okay, on page 5 in the note. Right. Now let's move on to the Ampere law, right? The fourth equation here. So the Ampere law, circuit law, again came from experiment. And then what Ampere kind of discovered at the time is that, okay, if you have a current, okay, if you have a current going through a wire, then if you put a magnet next to it, okay, so whenever he turned on the current, okay, the magnet will actually change its direction, and then when he turns it off, it will change again. So it's like the current, okay, will establish a magnetic field that can, put a force on your magnet. And then the law that he, the law that he summarized is that, again, it's actually very similar. If you do an integral, okay, of the magnetic field along any enclosed circuit, the sum, okay, will equal to a constant mu, and then sum of all the current, okay, inside this circuit, right? So if you have a field, okay, like this, I1, I2, okay, you just sum them up. Okay, so this is the original equation, and now of course you can kind of change this side into a surface integral by defining the current density, right? The sum of all current inside here will also equal to the integration of current density, which is defined as your current in a certain area the unit current in unit area. Say A here is a small area, okay, ds. Okay, so the surface density of the current integrate over the entire surface will give you the total current. Okay, so again, okay, you can clearly see that these two equations have very similar form, right? And then you can apply the Stokes theorem on the left hand side again, and then you will get, you apply same analysis, then you will get this, right? The curl of magnetic field will give you, is equal to a constant times the current density. 1 second. Now, so what this tells you is that the current, okay, can generate magnetic field, but in experiment, no one, okay, has actually discovered whether the electrical field can generate magnetic field. Okay, before Maxwell actually wrote down his equation, nobody have seen that in the experiment. Okay, so why Maxwell will add a term here? Okay, there are actually two. Well, the argument here is for him is kind of simple. Is that he believes there's some kind of symmetry, okay, between the magnetic field and the electrical field, right? So if you can generate the curl of electrical field from the time varying of magnetic field, then you should be able to do the same to generate a curl of magnetic field from a time varying electrical field. Okay, that's kind of a very simple belief. And then what he actually does is that he go on to do a thought experiment, which looks like this. Okay, this is a thought experiment. So what he does is that, okay, there's a current flowing from down to up, flowing up, and instead of really connecting the current, what he does is that he thinks, okay, maybe I can insert a capacitor, right, in between them, two metal plate, right, and you can see here is that the magnetic field down here. There's magnetic field down here satisfying the Ampere law. And then there's also magnetic field up here that's actually identical to below, right? Because it's the same current. So the question here is that, or the argument here is that, since from a suppose you're looking at the system from a very far distance, it looks to you that the current is actually continuous, right? Flow from here, and then there's a lot of charge accumulated on here, and then negative charge accumulated on here, and the current keep going up, right? So the argument is that maybe the magnetic field should also be continuous, right? Should also be continuous. Maybe there's also magnetic field here, okay? Magnetic field here. So let's see how this will play out. Okay, so the assumption here is that Maxwell's assumption here is that the magnetic field here inside the capacitor should be identical to the magnetic field, okay, around the current. Okay, he argued that these two should be the same, and whether it's same or not, you have to do experiment to verify. Okay, but following this argument, then what you will see is that first we write down this equation here. Okay, this is Ampere law, and in between here there's really no current, right? So there's need to be a way to write down this current. One thing you can think of is that all of this charge, okay, inside the current will be accumulated on the metal plate, right, in your capacitor. So what's really changing here is the current density, current surface density on the metal plate on your capacitor, right? The positive charge will go up here, also the negative charge will go up here, right? So that's a time varying term. And then we know that this charge will actually build up electrical field, right? Whenever you have charge, there's electrical field. So there should be a time varying electrical field here, and that could possibly lead to this term here. And then the derivation, okay, is relatively straightforward. The first thing that we need to figure out is what is the charge density, okay, surface density on the in the capacitor. And the definition, well, this is kind of straightforward. The definition of charge density is the number of charge right, the number of charge in per unit area, right, per unit area. And then we know that the current okay. Now let's look at what the time varying, okay, of the charge density would be. It would be d dt, okay, and then d dt, right? Because we know that the actually it would take the varying of the charge density to induce a time varying electrical field, to induce a curl of the magnetic field, right? So the time varying of the charge density here equal to this, equal to that. And then because this differential is on the time and this is on the space, so you can actually reverse their order. Okay, you can put the time differential in there. So instead of the unit charge divided by the unit area, it becomes the unit charge time varying of the unit charge divided by the unit area, right? And okay, and this dq dt, okay, it's just current, right? It's just current. That's the definition of current. Is how many charge flow, okay, per unit area. So this is just current versus an area, and this is just current per area, okay, give you current density, right? So these two are the same, right? So d dt equals j, okay, equals j. And the next thing is that you kind of want to know what this current density will give you, what electrical field, okay, the current density will give you. And this one, I think you guys should have solved it in the EM field class, where you treat the magnetic plate, where you treat this metal plate as infinitely large, and then you apply the Gaussian law, and then what you will get is that you will get, if we use the electric displacement field, then you equal to the charge surface density divided by 2, okay, divided by 2. And I think we'll have a homework on this just to derive this simple equation. And then the same is for the plate up here. And then you can kind of see that because the direction is the same, right? The positive charge have electrical field this way. The negative charge will also have electrical field this way. So the total electric displacement field will equal to, and we're assuming also equal minus, right? Just assume that there's a symmetry here. Then D will equal to sigma, okay? Sigma, or sigma plus, or sigma minus, or sigma. They're all the same, okay? Then with all this, okay, if we assume the magnetic field inside, okay, inside capacitor is the same as the magnetic field here with the current, right? Then this should still equal to mu j, and then as j equal to the time varying of the charge density, then it's also equal to this, right? Okay, so this is inside, this is outside the capacitor, this is inside the capacitor. So now it's very clear. Okay, if both of them are true, then this effect, they should add, okay, to each other. Right. Outside the capacitor, this term is 0, then you have this term contributing, give you a magnetic field. Inside the capacitor, you don't have any current, but then you have a time-varying electrical field, so that you also generate an identical curl of the magnetic field. Okay, so this is, so for Maxwell's equation, Maxwell's contribution, okay, one is that to write them all in differential form, okay, a very unified format. And the second is that he added the term that generate magnetic field from time-varying electrical field. And third contribution, okay, we're going to talk about here is how he used this Maxwell equation to predict the EM wave. Okay, any questions? Okay. Now the final thing, okay, before we go into the light and matter interaction, okay, is to quickly review the wave equation, EM wave equation, or the equation of light, okay, from the Maxwell equation. And I think most of you should have seen this before, but it really doesn't hurt to kind of revisit it again, okay, before we start anything serious, right? So for the wave equation of the light, right, one thing that we kind of, must have noticed is that when you generate a light, when you generate a beam of light, the propagation of light actually doesn't depend on whether you have charge in the space, right? The light can actually travel in vacuum, for example. That's why we can see the sun or the stars. So it really doesn't matter whether you have charge or not here. And the second thing is that when the light starts to propagate, okay, the current also doesn't matter, right? In most free space, the current is 0, so you can still see the electrical EM wave, propagate. So to make things very simple, okay, actually starting from here and in all of our classes, in all of our lectures, we will simply assume rho free, okay, equal to 0, and then J equal to 0, right? Especially when we consider when the light has already been generated, and then it's just propagating and interacting with other matters, right? And when you have this, then the equation become very simple now. You have E equal to 0, B equal to 0. The divergence of these two is 0, and then you have the curl of E, okay, same as the, and then you have the curl of B, okay. So here, just to show you guys the EM wave, okay, we'll make it, we'll simplify things by just assuming that we're in a linear situation where the displacement field and the actual electrical field is only off by a constant, right? By a constant. And in vacuum, okay, the constant is epsilon 0. That's the permittivity in vacuum. And then in media, for example, in water and then in glass, in other things, you will have a relative permittivity which is usually larger than 1. Okay, so we simply use this equation just to show, okay, how light propagates in a uniform media. So we plug this into here and set J to 0, then you have mu 0, epsilon 0, epsilon r. Okay. So Maxwell equation is actually a very standard coupled differential equation, right? You have magnetic field convert to electrical field, and then electric field convert back to magnetic field. It's actually the same structure as kind of a harmonic oscillator, right? Harmonic oscillator, you will have kinetic energy convert to potential energy, and potential energy convert back to kinetic energy, right? The only difference, or the difficult part in the Maxwell equation, is that it's first 3-dimensional, and second it's a curl. Okay, it's not a very simple differential. So whenever you see a coupled differential equation, the first thing you want to do is to just cancel one of the variable, okay, and then solve equation for just one variable instead of carrying 2 variables everywhere, right? And if you look at here, the simplest way to cancel out B, okay, the magnetic field, is to do a second curl on the Faraday equation. Okay, you can do curl on both sides of the equation. Okay, it will look like this. Curl on both sides, and then we know that curl is an action on position on space, and differential of time is time, right? So these two are independent, so you can switch, okay, the order, right? So you can do the curl first and then do differential, time differential. Okay, and once you do that, you clearly see that, okay, this term here is just this term, right? You can plug in this equation back to here, and you will get, okay, minus mu epsilon r. This is one differential already on time, and this is the second one, so okay, twice differential second, okay, of the electrical field. Okay, so you can kind of see that there's a symmetry here between time and space, right? You have second order differential on time, and then here you have 2 curl. 2 curl is also second order differential, right? And so now the only problem here, okay, or the only thing that's stopping us from solving this wave equation is, what is this, right? What is this? And for this, the simple way to kind of to know this is just to look into mathematics table, and then people have figured this out, hundreds of years ago, and then you can actually see that this is equal to okay. So what it does is that it kind of because the curl is a difficult calculation, right? Because if you do curl, if you have, let's say your electrical field is on x component, right? It's on x direction, then the curl can actually change it to y or z direction, right? So curl is something that you don't want to carry around in your differential equation. So kind of, it's better to change that into a dot product, or change that into a divergence, right? So if you look at this, okay, you think, okay, there's a lot of operator here, and then how can I really calculate it? And the way that you should do, okay, whenever see this operator, is to understand that, okay, the definition of this is that this is a vector, okay, you on x you do differential of x, on y you do differential of y, on z you do differential of z. Okay, and also the other way to write it down is ex representing the unit vector on x, and then ey. Okay, so if we take a look at this, the dot product of a vector operator and a vector, will give you a number, right? So this will actually give you a number. And then this is a number. Of course, the number has x, y, z as a variable, and then you have this operator, which is a vector, act on a number, it will give you back a vector, right? Because you have to do differential, x, y, z, right? So overall, this is a vector, which makes sense because this side is also a vector, right? Here you can also kind of see that the operator square would be delta times delta, then you just two vector multiply together, then this will be become a number, or become just an operator without no longer being a vector, just an operator, right? And this act on a vector. This is an operator act on a vector, it's still a vector, right? So you have on the right hand side a vector, on the left hand side is also a vector. So one thing you will see, us doing this, all the time in this class is that, ideally you can kind of solve this, in some way once you define the structure. For example, for a fiber, for a waveguide, or anything like that, you can kind of solve this analytically. But then to make our life much easier, we usually try to solve it in the simplest situation, right? So the simplest situation would be, it would be nice if this term is 0, right? If this term is 0, then you're only left with something like this, and this is kind of much easier because it's just second order differential on a vector, right? So when would this be 0? You can kind of show that at least a very popular case, that's a plane wave. For plane wave, if the wave is propagating along z direction, and then your electrical field is pointing to x direction, the oscillation is at x direction, and then propagation is on z direction, and this is something called a transverse wave. Transverse wave is that the oscillation direction is perpendicular to your propagation direction. And there's another wave that's longitude wave, right? It's, for example, the sound wave is longitude wave, that the oscillation of the molecules in the air, is actually the same direction as the sound propagation direction. So for transverse wave, you can kind of prove that the the dot product, the divergence of your electrical field has to be 0. It has to be 0. You can also kind of plane wave. You can also kind of prove. This term is much smaller than other terms for most structures. For most structures, not for every structure, for most structures. But we will not go into detail here. So transverse wave, in other words, is also called plane wave. Plane wave. For example, the light from the sun, can be treated as a plane wave. It's because it's so far away from us. It's a point emitter. And then when the light, propagating, it's actually a spherical wave going out. But then when it hits us, because it's so far away, we wouldn't see the curvature, of the sphere. We'll just see it approximate to a plane wave. plane wave. Then we can take this to 0, right, to 0. Then the equation, okay, become much, much simpler. It's now E, okay, and then, yep. Okay, there's a minus sign, there's a minus sign. So it will be minus sign equal to minus sign. Okay, and you can kind of move it, you can kind of cancel this minus sign here, and then you can move this term to the left, and there's a minus sign, and then equal to 0. Okay, so this is kind of a very standard wave equation now. Okay, wave equation now. And probably we can, yeah, okay. And so to make life even easier, okay, what we would do is that we assume, okay, we already said that we assume the electrical field, the wave is propagating on z direction, the electrical field is pointing to x direction, so that when you write down the E, what you will see is that you only have an x direction component, okay, and as wave propagate along z direction, so this electrical field should be a function of z, right? Should be a function of z. For example, if the light attenuate as it propagate, then your amplitude would decrease, right? And of course, because it's a wave, you can kind of think, okay, this is also a function of time, right? Because it has to oscillate with time. Okay. So now when you plug this in here, then what you will have is that okay, the differential on x, y, z acting on this vector, and this vector is only a function of z and t. Okay, and you can see that this two term, okay, it doesn't really do much because there's no x, there's no y dependence of the electrical field on the position of x and y, right? And minus, okay. So then what we can do is that, okay, we can carry this over, then you will have partial z, okay, E. At this point, it really doesn't matter if you leave it as a vector or you write it down as a number of variable, right? Because here, well, in this case, it's very simple, okay? Because this is simply an operator act on a vector. It only changes the magnitude of the vector. It doesn't change the direction, right? So in this way, you can kind of see that these two terms are always the same. The vector is always pointing to the same direction. Well, not the same direction, always pointing along the same direction, right? It's x direction, okay? It can be up or down, but then there's no y or z component, right? So if you write this, it's fine. If you erase this vector, it's also fine, okay? And for a differential equation like this, okay, this is very, very standard. Probably you guys see it before. Have seen it before. Okay, you have second order derivative on position, and then you also have second order derivative on time, right? And then there's a very standard solution for this. And for differential equation, okay, usually this the way that you actually solve it is that you kind of, unless you use some advanced trick, otherwise you just have to guess a solution, Okay, you have to guess the solution, and then you plug it back, and then verify it. And for this very standard wave equation, then the solution is very simple. Okay, you have, okay, there's a vector. It doesn't really matter here. And the amplitude, okay, you have amplitude here. And then the solution is cosine omega t minus kz. Okay, cosine omega t minus kz. You can see here, because the equation itself is linear, right? It's linear. If you increase the magnitude of E knob, right, the amplitude of the electrical field, this term will increase the same amount as this term, right? So it really doesn't matter, okay, what your amplitude is. The wave will propagate the same way in a linear situation. And then the cosine here, you can kind of see, okay, if you plug it back, first time derivative will give you sine, okay, minus sine. And then you do derivative again, and they give you back to cosine. And same here, okay, if you do the derivative of z, and then second derivative of z will give you back to cosine. So you can also kind of see that, okay, this solution, you can add a lot of variation here. You can, add a phase term here. Okay, it's still a solution because you still have sine and cosine. And then also sine is also a solution. Okay, sine is also a solution. Okay, so it's this equation, when you're writing down like this, it provides you a set of solutions that show you, okay, what could be the possible solution for light. Okay, what could be the possible solution for light? And now let's spend about 10 minutes to kind of look into what is omega, what is k, and then what is the speed of this wave, and then we can kind of let you guys go, and then next week we will start to talk about light and matter interaction. Okay, so omega here is very clear. Omega is, by definition, the period, right? If the period, is a frequency, angular frequency. So if the period of the wave is t, okay, it means that at any certain point after time t, your magnitude go around one cycle and go back to its original magnitude, right? T equal to 1 over f. F is the, put it this way. T is the period, and then 1 over t is the frequency, right? It's the frequency. And then angular frequency is just 2 pi times f, right? Or the other way you can write it is f equal to the f omega divided by 2 pi, okay? And then the reason that we write omega here instead of f here is that for cosine, the period is 2 pi, right? So for it to change one period, okay, it will change from 0 to 2 pi, and then your cosine will repeat its value, okay? So this is the definition of omega. And then k is kind of you can kind of think of it as the omega in space, okay? It's how the wave repeats itself, right? So let's complete this drawing here. So for wave, you can kind of define this is its wavelength, right? After a certain distance, the wave, okay, repeats itself. So lambda is actually the wavelength. It's the period that it repeats itself in space. And then apparently, okay, if you do 1 over lambda, it will give you a frequency, okay, in space, right? And then if you times 2 pi, that will just give you the angular frequency, okay, in space. Okay, equals k. So this is the definition of k, okay. And of course, you can define it in different way, right? Like this is, there's no hard requirement, right, in terms of mathematics, right? You don't have to define k in this way, you don't have to define omega this way. But like over the years, people have found it, okay, this is the easiest way to use this equation. And so everyone kind of all agreed on these notations here, right? And there's a link between, okay, the omega and then k is linked by this definition, okay, of wavelength. And what is wavelength? Right? Wavelength, you can think of it as the wave propagate, the distance of the wave propagate in one period of time, right? If the time is t, and then the speed of the wave is, let's say, cr, okay, speed of light, r describing the relative, okay, cr, then this is also k, right? Because this is how you define wavelength. Another way that you define wavelength. And then now if you look at this here, okay, 2 pi divided by t is simply omega. Okay, so there's a relationship between k and omega once you define your waveform, okay, in this way. Now, let's now finally, okay, plug this back into our wave equation here. Okay, because there's some coefficient here, so there should be a separate relation between omega and k. Okay, so if you plug it back, and then okay, these all terms they cancel each other. So cosine the differential of t, differential of z, okay, give you k squared, okay, k squared, and then there's a minus sign here, but there's also a minus sign here, so we kind of don't care about them. K squared cosine omega t minus kz, and then here is minus sign mu and then differential of t, so it gives you omega squared. Okay, and it's also cosine, okay, equals 0, right? So if you compare this equation, what you will get is k squared equal to mu epsilon r omega squared. Okay, you get this, and then if you look at it here, you will also have k equal to omega divided by the speed of your wave, right? Speed of wave. So by comparing these two equations, okay, both of them has to be true. So if you compare these two, you will get your speed of the wave is 1 over mu epsilon, and then 1 over epsilon r, right? So this okay. So this part here, okay, this part here, 1 over square root of mu naught epsilon naught is the speed of light in vacuum, okay, speed of light in vacuum. And then this part here is the refraction index, right, refraction index. So the usually people define refraction index as how much the light will slow down, right, how much the light will slow down. And then from here you will see that there's a connection, okay, by doing the Maxwell equation, you will see that there's a connection between epsilon and n, and then you have epsilon r equal to n squared, right? This is where this equation comes from, okay? So that is it for today, and then when we come back next week, we'll start to, really focus on, okay, what, where this linear equation come from, and what is the difference between, charge and free charge, and then also show you guys, okay, how the matter really respond to light. Okay. Okay, that's all for today. I'll see you guys next week.